Okay, Robert.
Okay, so thanks, Mel, for the chance to speak. It's a pleasure to speak at CANT this year. So I'm going to talk about a project that I've been working on with a postdoc here at Stony Brook, Yoon-Hae. It's a subconvexity problem for Shintani zeta functions. So just to motivate the talk, I'll point out a couple of problems in arithmetic statistics. So there's theorems of Dillon-Faddeev, Gangos, and Savin, and then from Bargowitz thesis, classified integral orbits in what are called pre-homogeneous vector spaces. So you have SL2Z acting on binary cubic forms is a classical result going back to Dillon-Faddeev is in bijection with cubic rings of isomorphism, and then Bargowitz proved that orbits pairs of Chernay quadratic forms are in correspondence with discriminant preserving correspondence with quartic rings and cubic resolvents of isomorphism, and then there's another. If you take four alternating forms in 5 variables, there's a correspondence with clinic rings with a sexic resolvent. So those are all part of Bargowitz's work. So these are examples of problems where integral orbits in something called a pre-homogeneous vector space. So are parameterizing arithmetic objects that we care about. So so if you study the distribution of the orbits, you can understand more statistics regarding counts or other statistics that you care about. So for instance, if you think sieve rings, you can reach fields and count fields or other properties of fields. There's been a lot of work in this area since Bargowitz's thesis, studying arithmetic statistics. So I've been working with a couple of collaborators, Frank Thorne, Takashi Taniguchi among them, studying more analytic approaches to this problem. So I'm going to tell you a little bit about that today. So just to explain quickly what a pre-homogeneous vector space is. Be a real Lie group. So and then I'll think of the integral matrices within a group as GZ. And then VR is a real vector space. With an action of GR. Okay. So just for example, later cubic forms. F of x. Y is ax cubed plus bx squared y plus c x plus b. Say GL2 x as g dot f of y is equal to f of y divided by the determinant. Okay, so then under this action, the space VR is a disjoint union of orbits. So a set S is a singular set. So we have an invariant flow discriminant in each space, and then disjoint union GR 1. These are open orbits. With finite stabilizer. Which we'll view as a homogeneous space. So there's a Cartesian structure on the vector space, but then there will also be a sort of a set of homogeneous coordinates coming from the Lie group action. So you could view each orbit as a homogeneous space and put homogeneous coordinates on the space. So so e.g. for binary forms. There's a v plus and v minus corresponding to plus and minus discriminant. So n plus 3, it's 1, the stabilizer. In G plus, which is G in GL2R. That's the determinant G positive. Okay, that's sort of fixed out. So going back to the 70s, there are papers of Sato and Shintani. Produce zeta functions. Integral orbits. Homogeneous vector spaces. By discriminant. So e.g. H of M is the class number of the binary. This one. These zeta functions are still somewhat actively studied. So the best studied is the Hough case, which Shintani gave a functional equation. The residues, residues. And then there have been a number of authors since who have developed the other cases. Maybe most obviously UPA. Case. Right. There are dog treatments, but many of the analytic properties are still unknown. So what Hough and I have developed is a way of proving a subconvex bound for these zeta functions in the critical strip. there's zeta plus over so gamma is SL2Z binary cubic forms. Zero. The generating function is one of the stable is absolutely zero paragraphs. There's also I've also so in this case, P is a Heck eigen class. And then there's using the homogeneous description, there's a way of evaluating the cusp form on each form. So now we have cusp form on the binary cubic form. So the original cubic zeta function has a present functional equation. We find zeta add is root 3 zeta plus the zeta function over positive discriminant forms plus zeta minus and zeta sub plus zeta minus. And then they're completed zeta functions. So completed one. There's a four. And then 4 gamma factors. These are like degree 4L functions, but they don't have one of the properties. So they don't satisfy the Riemann hypothesis. They're zeros of the functions off the critical line. So they don't have the other product. These satisfy a self-field function equation. Okay. So there's a convexity bound for the zeta functions in the critical strip, which interpolates using Franklin-Lindelof between the domains of absolute conversions for the Dirichlet series. So in this case, the convexity bound grows like T on the half line. So we'll prove a subconvex bound. Overall. Zero as infinity minus is bounded by say tau. We'll say just a little 99, 98 or 99. Fine. Yeah, that's a subversion. actually see a little bit better. The cusp form is useful on the cusp, so it kills all the terms on the cusp. So the theory for these, in some ways, so a functional equation is not currently known for this twisted version. There's an obvious one. So we have some way around it, and so it's so it's not obvious what the convexity bound is a priori, but it says the same convexity bound actually. And in some ways, they're much better behaved. You don't have to deal with the forms of the cusp. So let me just make 4 remarks. The discriminant is a degree 4 polynomial. Who's the US on the composition? This factor is a matrix in GL2R as our G plus as a G is equal to T lambda U A T A theta, where D lambda is equal to this multiple surface identity. Then U, the unicorn subgroup. AT. And then it is rotation. Okay, and then was a partition of unity support on a single set. Is supported. Single set. SAP. So let F P a determinant as a bar. I'm going to use this to restrict to forms in a fundamental domain. Here, this is equal to matrices NU, AT, A theta, where U is equal to A and T is equal to C. That's a simple set. Assume that partial U F and partial T F bounded. Okay, and then this gamma F gamma times G. Ready? I have time to just give you a sketch of the proof. So using the approximate functional equation, reduces to some of the following type. So there's a smooth weight. Where so this is a smooth weight that truncates the sum of this length essentially t squared. So it's a degree 4 zeta function. So you can write essentially the sum of two sums in the critical strip of length t squared or tau squared. So we use so Vargava has these counting results for these problems, and you use an averaging trick of the counting to trim off the cusp. So here K will be a compact. So sigma is equal to the expectation with respect to some weight of the locus of the weight, which I'll just hide. And then there's a sum over G dot P is equal to F. The theorem. So with respect to this expectation, the number of forms such that the discriminant is less than or equal to X, and in the US Saudi decomposition, T is less than or equal to T is equal to X. Now, by the Davenport-Halpern theorem, the number of forms of this coordinate is X is order X, so you save the vector of T. So this reduces essentially from X set B less than or equal to T less than in the US Saudi decomposition. Well, I'm roughly out of time, so I'll just quickly say what else was improved. So I introduced a second average over the form. So once we've truncated to, you have this fundamental domain, and you now cut at T, and so the change of variables between homogeneous coordinates coming from the group and coordinates in the Cartesian coordinates in the vector space is now controlled. It's bounded. So we estimate. Is tau log of this plus y. So this is a degree 4 polynomial. The discriminant is degree 4 polynomial. So we apply the Taylor expansion. So Taylor expansion. Plus 2 applications of interpropet. That's just a small part. That's essentially what those are the proof. So I'll essentially stop there, but just say the word, say an extra word, which is that there isn't a known functional equation in the twisted version case. So it's not obvious what it would be, but we can still prove a representation like this, in which this has some group dependence, and we're able to nail down the group dependence using oscillatory integrals to control where the group evaluation occurs. So I go into that. And then the method is roughly general, so it would work in a different, for the zeta function of a different pre-homogeneous vector space. So, okay, I'll stop there.
Thank you very much. If there are any questions, I will look in the Q&A. But if not, I thank Robert again.
Right, thank you.
And